Hi guys, Mrs. Yukin here. I'm going to go through notes 9.1 with you in case you missed them for any reason. So today we're going to talk about graphing polar coordinates. Up until now, everything we've been graphing is on the coordinate plane. Our points have been in the form x, y. Those are known as rectangular coordinates. But not everything is rectangular. The Earth, no matter what anybody tells you, is round, and so sometimes it makes sense to use something called the polar coordinate system. So the polar coordinate system is going to feel familiar to you because it shares a lot of characteristics with the unit circle. So it's not totally unfamiliar, but it does have some differences. So its origin is a fixed point, O, called the pole. So you can see it right down here. And then there's only one axis. It's the polar axis. It's a ray that emanates out from that pole in the positive horizontal direction typically. So if we want to locate a point, for example, this point P down here, then what we use to locate it is we say how far away it is from the pole, that is our radius, and then we say at what directed angle is it. And that directed angle is going to be similar, in fact it's going to be the same, as the angles we used on the unit circle. Now the unit circle had a radius of 1, so we never really said it's 1 unit away. But essentially, when we were naming points, we were using something not all that different from this polar coordinate system. So just like on the unit circle, when we graph, a positive value of theta indicates a counterclockwise rotation, and a negative value indicates a clockwise rotation. There's a little bit of a wrinkle here in that now we can have positive values of r, which means that my point is on the terminal side of my angle, so on the same side as the ray that we would draw. Whereas if we have a negative r value, a negative radius, then we're on the opposite side of the pole. We're in the opposite ray from where we would expect it to be based on the angle that we're given. And that'll become clear as we go ahead and we graph. Let's go ahead and graph a couple points so you can see what I'm talking about. So we've got our origin, we've got our ray, that is our polar axis. And then for this point here, we've got a radius of 1 at an angle of 200 degrees. Normally when we graph, we're going to go ahead and give you a polar graph, but this time we didn't. So I'm going to go ahead, I'm kind of going to make an axis so I can orient myself to 200 degrees. So 1 unit out, let's say that that's right here, and I'm going to come around to 200 degrees. So here's 90, 180, and a little bit past 180. This would be my ray. That is the terminal side of the angle. So there's my 200 degree ray, and then my point is 1 unit out. So this point right here is my point S, which is what I was graphing. All right, let's go ahead and do the same thing. Obviously that was in degrees. We can do it in radians also. And so I've got my origin, I've got my polar axis. Let me go ahead and give myself some orientation. So here's 2 units out. And then we want to come around to 3 pi over 2. Right down there is 3 pi over 2. Okay, normally that would be where my point is located, but because of this negative 2 value, instead of being located on the same side of the pole as my terminal side of the angle, it's actually going to be on the opposite side. So I'm going to go ahead and flip my point up here, and that is going to be where point R is, at negative 2 on the opposite side from 3 pi over 2. So it's actually a pi over 2. Okay, let's graph some points on a polar grid, which for those of you who are artistically challenged like I am, well, you will find this much easier than what we just did. So you'll notice if you look at these 2 grids here that we can either have polar grids that have radians for angles, or we can have polar grids that have degrees for angles. And then you'll also notice that now we have rings on them, and the rings come out from the positive x-axis and are labeled 1, 2, 3, 4, 5. So that's easier to figure out where you're going. And so let's look at point A here. Point A is the point 3, 5 pi over 6. So it's 3 units away from the origin at the angle of 5 pi over 6. I like to start at the angle, so there's my 5 pi over 6. I'm going to go 3 units out from the origin in that direction. So 1, 2, 3. That is where my point is located. Point A. Voila. All right, let's look at B. Now you'll notice, those of you who are astute observers, that B is slightly more challenging because both the radius and the angle are negative. So let's talk about how that works. So negative 240, that means I'm now going clockwise from my origin. So I'm going to go this direction until I get to negative 240, which is right here at a positive value of 120. And then my negative 2 for the radius means that instead of going 2 towards that 120, I'm actually going to go 2 in the opposite direction, which means it'll be across the origin from the ray that would normally terminate at 120. So this is my point Q. And those of you who have already thought ahead have realized that, hey, can't I just call that point 2, 300? Because that's where it's located. And my answer to that is yes. Just like on the unit circle, there are an infinite number of ways to name coterminal angles, so there are actually an infinite number of ways to name our polar coordinates. And we will frequently ask you to give us a number of other ways to name it in this unit. For those of you who are big fans of process, that means if I have this point r theta, I can also describe it as r theta plus or minus any value of 360 or multiple of 360, or if I'm doing it in radians, I can do theta plus or minus 2 pi. And then I can also get fancy and I can do negative r, and then I can change my angle based on that. Let's take a look at example 3 here. So we are supposed to find 4 different pairs of polar coordinates that name the point S, and then they limit us to between negative 360 degrees and positive 360 degrees. And that's just because we could come up with way more than 4 if we weren't limited. And notice that we have to stay in degrees because that's what it's specified for theta. So I think the most obvious one is the one where we look at point S here and we say, okay, it is on the ring that has a radius of 2, and it is at an angle of 210 degrees. But I could also say that if I keep my r value positive at 2, now I'm going to do my negative angle, and I'm going to go clockwise negative 150 to go ahead and get that value. And that's the same thing I would do if I did 210 minus 360. Now if I added 360 to 210, I'd be outside of my allowable range for theta. And if I subtracted 360 from negative 150, I'd also be outside my range. So there must be something else that I need to do now. And that's something else to say, okay, well, what happens if I make my radius negative? So then I need to look at the angle I am across from. So point S, if I use a value of negative 2, it is across from 30 degrees. So I could also say that is negative 2 comma 30 because it's on the side opposite of the pole from 30 degrees. And then I need to go ahead and add or subtract 360 from that 30 to get my fourth angle. Well, obviously if I add 360, it's going to be too big. So I need to go ahead and I need to subtract 360. So I'm going to get negative 330 for my final and fourth point in that range of theta. So let's talk about graphing polar equations. Today we're going to stick to the really easy stuff. We just learned how to graph a point, now we're going to learn how to graph the two very most basic graphs in the polar coordinate system. So the first kind is of the type r equals some constant, and it represents all of the points that are that constant away from the pole, therefore it's a circle with a radius of the constant, centered at the origin. The other kind of equation that we'll graph is theta equals k. So that's all the points that are on the line that make an angle of k with the positive polar axis. Lots of times kids, when they graph these, they only graph one side of it. It needs to be a line, not a ray. So make sure you go to the positive values and the negative values. All right, let's graph one of each of those kinds that I was just talking about. So my first one is r equals 2.5, so I'm going to come 2.5 out, and I'm going to graph all the points that are 2.5 points away from the origin. Did I mention that I am artistically challenged? Because this is about to be a terrible circle. All right, here we go, 2.5 points out. It does not help that I'm doing this on an iPad. Wow, that is awful, but you get the point. Math pun. Okay. The next one we're going to graph is we're going to graph all the points that lie along the line theta equals 5 pi over 6. So I locate 5 pi over 6, which is this direction, And it's all the points, so it's the points in the opposite direction from it also. So it makes a line, not a ray. That is how easy it is. Okay, let's talk about our final concept for this lesson, which is the polar distance formula. If I am given two polar coordinates, then I can find the distance between them by, which by the way is annotated, they just put P1, P2 next to each other, by this lovely formula right here. Is that formula looking at all familiar to you? Because it really, really should. It should look very much like something we just did. Let's plot some points and talk about why that formula should look so familiar. So if I have my point 8, 60 degrees, you know what? I'm going to modify this grid so that my scale is 2 for every one. So I'm going to make this 2, 4, 6, 8, 10. All right, so 860, so I'm going to come out to my ring of 8 at an angle of 60 degrees. There is my point A. And then 4, 300, so out here at 300 at my ring of 4, there is my point B. And I want to know the distance between these guys. Well, this guy is at that angle, and this guy is at that angle. And oh, look, it's an oblique triangle. That's right, folks. This distance between the point is the side across from a known radius and another known radius and the angle that is between them. That, my friends, is the law of cosines. So you need to memorize this, but good news is you've already memorized it because you've got the law of cosines down. So how far apart are the two airplanes? All right, let's do this thing. The square root of my first radius, which was 8 squared, plus my second radius, which was 4 squared, minus 2 times the product of my two radii, times the cosine of angle 2 minus angle 1. So I've been using B as my 2 and A as my 1. So that winds up being 240 degrees. And you'll notice that that's not actually the angle that I drew in the picture, but it turns out it doesn't matter. It doesn't matter whether you use 240 or the angle in the picture, which is 120. You're going to get the same result. Crazy how math works. All right, and then you punch that all into your calculator, making sure you're in degree mode, obviously, if your angle is in degrees. And I have just realized that I did not bring my calculator home with me in order to make these notes. I did a quick version of this problem on my iPhone, and I got about 10.6. Oops, sorry, didn't mean to move that. I got about 10.6 miles. I'm hoping that's right, but if it's not, you should type it into your calculator, and you should double check me because, you know, iPhone and all. All right, that is all there is to Notes 9.1. That was not so bad. You guys should go ahead and you should do your homework, and then you should ask if you have any questions. Have a lovely rest of your day.